Welcome back to the lectures on higher order functions. We just looked at the mother of all higher order functions over list, fold R. And we will end this section with a few other standard higher order functions that are available in the Haskell library. And one of those functions is function composition. And function composition is another fundamental operation in functional programming. Functional programming is programming with functions. And if we have functions, we want to kind of combine two functions into another function. Just like addition takes two numbers and gives us a new number, we want to have a similar operator that takes two functions and combines them into a new function. Well, here's the definition of that operator, and it's written as dot in Haskell. So unlike object-oriented programming, where dot means invoking a method, in Haskell, dot means composing two functions. So in both cases, the dot is used for the most fundamental operation on the kind of objects that the language supports. So in an object-oriented language, we have objects and we can call methods on them. In Haskell, we have functions that we can compose. And here's the type. Function composition dot takes a function from B to C. There's the function from B to C. Then it takes a function from A to B, and it returns a function from A to C. Now, when you look at this type, it can be a little bit confusing, because there's the B is here as the output, and the B is here as the input. So it's kind of, seems to be that things are in the wrong order. But that has everything to do with the fact that function application associates. So here's the definition of composition. So what we do is we have two functions, and then we first apply G to X, and then we apply F to the result. Okay, so let's now see if those types make sense to us. The type of F here is a function from B to C. The type of G is a function from A to B. Well, then in that case, X must be a value of type A. So if we apply G to X, we are applying this function that takes an A into a B. So the result of applying G to X is B. Ha! And that fits into here, and we get a C. So let's look at the return type here. We get a value of type A, and we return a value of type C. All right? So at first, that type might look a little bit confusing, but once we figure it out and we kind of, we use the fact that function application here associates to the right, everything falls into place. And here's an example of using function composition. Suppose we want to define the function odd that checks whether an integer is odd. Well, odd is defined as not even. Well, there we go. The definition, it says, first check whether it's even, and then invert the result. And this definition here, this is what people often call point-free style. Because the other way we could write odd would be lambda x, even of x, not of that. But now we have a lambda and parentheses, so that's kind of a little bit verbose. And a lot of functional programmers prefer to use function composition to remove all the lambdas and the parentheses. But I have to warn you, and I'm guilty of this too, when you just start using function composition, you're trying to use it everywhere. And it becomes a sport to write things in point-free style and write them very compactly. The price you pay is that it becomes very hard to read. So now the people that read your code have to undo all this function composition in order to understand what's going on. And typically, when they understand what's going on, the light bulb goes on and say, okay. But I think it's better to kind of use function composition sparingly, because you always have to write code for others to read. okay? So you don't write code to look cool yourself and see, oh, look, I can do this point-free style. Plus, there's automatic programs that make things point-free for you, so you're not as cool as you think, okay? So use function composition sparingly, and don't go bananas with function composition. Okay, here are a couple of other functions that are in the standard library, higher order functions. These are, most of them are defined using fold_r or using comprehensions. These are all interchangeably. I prefer using fold_r. Some people prefer list comprehensions. The reason I prefer fold_r is that fold_r, this concept of folding over a data type works for any recursive data type, whereas list comprehensions only work for lists. We can use general comprehensions, but it gets all a little bit tedious. So at some point, it's just easier to define a fold function and then define other functions on top of that. All right, so, but let's just look at this one here. All is defined as map P of X to the list access, and then check whether every one of those is true. Okay, so a nicer definition of this would be map of P compose end. Any is the same thing. We map P of X, P over the list access, and then we call OR. So for example, if we want to check that this string here, ABC space DEF, contains a space, we can call any is space function from character to bool, and this will return true. Here's another interesting function, take while. Take while takes a predicate, and unlike filter, which goes through the whole list and throws away all the elements for which the predicate does not hold, take while is like a while loop. So it uses its predicate and chops off elements from this list and returning them until this predicate is false. So let's look at the definition. If the list is empty, well, what can we do? We can only return the empty list. In case we have a non-empty list, it looks like this, x cons x's, and now we have two cases. Either P of X does not hold, in that case we terminate the recursion by returning the empty list, and if P of X is true, there's a trapdoor here in the studio. Take while not fall through the hole. If P of X is true, then we cons X onto the recursive call of take while of P of X. So for example, they have a string, and we can take characters from this string as long as they are letters by doing take while is alpha, and then it will take ABC, and since the space is not an alphanumeric character, it will terminate right there. Dually, to take while, we have the function drop while that removes all the elements while a predicate holds. Okay, so take while keeps all the elements until the predicate is false. Drop while drops the element until the predicate turns false. So you see here that in this case it drops the value, and instead of returning the empty list there, it just kind of, puts the value on top of the rest. Good. Happy hacking, and make sure you do the exercises, because all the higher functions that we have seen here, like take while, drop while, map, filter, you will have to implement them in terms of fold_r. All right? And so please make these exercises. And if you're not using Haskell, say you're using Scala or Java, you can do the same thing. These languages typically also have fold_r. Maybe it's not called fold_r, sometimes it's called fold_right, or sometimes it's just called fold. But this idea of having a higher order function that captures the essence of recursing over a list is available in any library that supports lists. And for example, in C#, it's not even called fold_r, it's called aggregate. So that comes from SQL, where you're aggregating over a list. So don't be fooled by the name. The idea is what matters. And thank you so much, and see you next week.